Hello, today's lesson is going to be on a very special class of triangles, the right triangle. So the Pythagorean theorem, which we'll learn about in this slide, is probably the most famous theorem in all of mathematics. A triangle with a 90-degree angle is called a right triangle. The two sides that meet to form the right angle are called the legs of the triangle, and the long side opposite that right angle is called the hypotenuse. The Pythagorean theorem can be stated as, if the legs of a right triangle have lengths a and b, and the hypotenuse has length c, then a squared plus b squared is equal to c squared. This theorem today is named after the 6th century BC Greek Ionian philosopher Pythagoras, but it was known in China and India prior to his birth. There are literally dozens of proofs of this theorem, and one example is given on this page. So the earliest version of the proof I'm showing here comes from China. Let's arrange four identical right triangles with legs A and B as shown in this diagram. Okay, so we create an outer square with sides length A plus B and an inner square made whose sides are the four hypotenuses. So this square has side length C and area C squared. The total area of the outer square is A plus B, that quantity squared, and if we expand the binomial, that's A squared plus 2AB plus B squared. So this has to equal the area of the four triangles, which is 4 times 1/2 the product of the legs, and the area of the central square, c squared. So a squared plus 2ab plus b squared is equal to 2ab, that's where the 2ab comes from those four triangles, plus the central square, c squared. We have 2ab on both sides of the equation, so that cancels, and we have proven that a squared plus b squared equals c squared. So let's learn about Pythagorean triples. These are also called Pythagorean triplets. The Pythagorean theorem often leads to answers with square roots in them. We'll see some important examples later in this lesson. Math contests, though, typically like clean answers that emphasize your grasp of the math and don't get bogged down with calculations. This is why Pythagorean triples show up in math contests so often. Pythagorean triples are sets of three integers that satisfy the Pythagorean condition that the sum of the squares of two integers equals the square of the third integer. One such triple is 3, 4, 5, since 3 squared plus 4 squared is equal to 5 squared. It will be helpful in contests to memorize the most commonly seen Pythagorean triples. These are 3, 4, 5, 5, 12, and 13, 8, 15, and 17, and 7, 24, 25. So in addition to knowing those four Pythagorean triples, keep in mind that if we multiply all the elements in a Pythagorean triple by the same constant, the resulting triplet still satisfies the Pythagorean relation. This is easy to show using the distributive property. Suppose we have three numbers such that a squared plus b squared is equal to c squared. What happens when we multiply each element by the same constant n? Does NA, quantity squared, plus NB, that product squared, plus the product NC squared, does it equal? Factoring out the common n squared, on the left-hand side we get n squared times the quantity a squared plus b squared, and the right side we have n squared c squared. We can cancel the n squared from both sides of the equation, and we show that we still have the relationship that a squared plus b squared is equal to c squared. So as an example, since 3, 4, 5 is a Pythagorean triple, 6, 8, and 10 is as well. Of course, the constant we multiply by can also be a fraction. Multiplying each element by 1/4, 3/4, 1, and 5/4 satisfies the Pythagorean relationship. If you want an algorithm for computing any Pythagorean triple, all Pythagorean triples may be obtained by taking any counting numbers m greater than n, and then if a is equal to m squared minus n squared, and b is equal to 2 times the product m and n, m times n, c is equal to m squared plus n squared. To prove this is true, just realize that m squared minus n squared is equivalent to m plus n times m minus n. And if you bear that in mind, it's very easy to show that this works. So let's move on to the converse Pythagorean theorem. If the square of the largest length in a triangle is equal to the sum of the squares of the two smaller sides, then that triangle must be a right triangle. So the Pythagorean theorem told us that if we have a right triangle, then a squared plus b squared equals c squared. The converse tells us if we have a triangle where a squared plus b squared is equal to c squared, then that has to be a right triangle. Well, how can we prove this? Let's construct right triangle ABC and another triangle, we don't know that it's right yet, DEF, such that the lengths AB and BC are equal to DE and EF. So by having one bar on both of them, we represent that AB is equal or congruent to DE and BC is congruent to EF. They both have the two bars. Since we are given the sum of the squares of the two smaller sides is equal to the square of the largest length, then the largest length of the triangle DF must be equal to the hypotenuse AC. Similarly, by side-side-side similarity, ABC is similar to DEF, so angle ABC is congruent to angle DEF, and therefore angle B is equal to angle E, so angle B was a right angle, angle E is a right angle, and triangle DEF has to be a right triangle. Okay. The relationship between the square of the length of the longest side and the sum of the squares of the lengths of the shorter sides can tell us if a triangle is acute, in other words, its largest angle is less than 90 degrees, or obtuse, its largest angle is greater than 90 degrees. Okay, if the longest side is C, if a squared plus b squared is less than c squared, then the triangle is obtuse, as illustrated here. Angle theta is greater than 90 degrees. Also, or on the other hand, if a squared plus b squared is greater than c squared, then this angle theta is less than 90 degrees, and the triangle is said to be acute. Finally, note that as theta, this angle, approaches 180 degrees, length C approaches the sum of A plus B. Okay, so just picture as this angle opens up, right, closer and closer to being a straight line, the side length C comes closer and closer to the sum of A plus B. Similarly, as this angle closes down, getting closer and closer to zero, side C length approaches zero. So now we're going to talk about the isosceles right triangle, also known as the 45-45-90 triangle, where these are the measures of the angles, 45 degrees, 45 degrees, 90 degrees. Okay, so we have the isosceles right triangle. So we have A and A. So instead of lengths A, B, and C, because this is an isosceles right triangle, A equals B, and we have lengths A, and C. Okay? Now, this obeys the Pythagorean theorem. We also, by the way, know this has to be 45 degrees because the sum of the angles is 180 degrees. We have a right angle 90. The remaining two angles have to sum to 90, but they're equal, so each is 45. Using the Pythagorean theorem, a squared plus b squared equals c squared, but b squared equals a squared. So 2a squared is equal to c squared. When we take the square root of both sides, it's easy to see that c is equal to the square root of 2 times a, as shown here. The diagonal of a square divides it into two congruent 45, 45, 90 triangles, right? All the lengths of the square are a. If we draw a diagonal, by symmetry, this angle is 90, this angle is still 90. These angles all have to be 45. So this is a 90, 45, 45 triangle. And this is a 90, 45, 45 triangle. And therefore the diagonal is equal to the square root of 2 times a. The area of the square we know is a squared. Note that this is equal to 1/2 times the square of the diagonal. So if there's ever a problem where you're given the length of the diagonal, you don't have to go back and calculate the sides to find the area. Just realize that the area of the square is equal to 1/2 times the square of the length of that diagonal. Suppose we have two intersecting diagonals. In that case, we divide the square into four congruent 45, 45, 90 triangles. Okay, each of them has a hypotenuse A. Okay, so each of their legs is the square root of 2 times A divided by 2, or 1/2 the square root of 2 times A. So now let's talk about 30, 60, 90 triangles. These are right-angled triangles. So one of their measures is 90 and the others are 30 degrees and 60 degrees. Suppose you have an equilateral triangle of side length S, as shown here. What is its area? Well, the first step in calculating this is we draw the altitude. It has length h. We know that the area of this triangle is going to be the length of the base, which is S, times 1/2 times h, but we need to find out what h is. So let's draw this perpendicular here, and by symmetry, this line, altitude, bisects the 60-degree angle, right? In the equilateral triangle, all the angles were 60 degrees. By symmetry, we bisect this angle and form two triangles, two right triangles, each with this top angle equal to 30 degrees. So we have created a pair of 30, 60, 90 right triangles. The area of an equilateral triangle of side length S is the square root of 3 times 1/4 times S squared. Why is this so? Using the Pythagorean theorem, this altitude by symmetry bisects the base. So this 30, 60, 90 triangle has side length S over 2, side length S, and side length H. So we can solve for H. H ends up equal to 1/2 times the square root of 3 times S. So 1/2 times H times S gives us the 1/4 times the square root of 3 times S squared. In a 30, 60, 90 triangle with hypotenuse length S, the side opposite the 30-degree angle has length S over 2. That's easy to see by symmetry. We know this angle is 30. This side opposite the 30-degree angle is S over 2. And the side opposite the 60-degree angle is H, and we said that was equal to S over 2 times the square root of 3. So it's easy to remember we have lengths S, S over 2, and the square root of 3 times S over 2. If you're trying to memorize all this, though, you can lose your way. So I don't necessarily memorize this. If I just remember how I derived these relationships, I could always quickly come up with them again. But it is very handy on contests to recall that the side opposite the 30-degree angle is half the length of the hypotenuse. So let's move on to something else you'll see a little less often in contests, but it's important nonetheless. What about right angles in the coordinate or the Cartesian plane? A very important theorem tells us if two lines intersect at a right angle, so they're perpendicular in the coordinate plane, then the products of their slopes is -1 unless the lines are parallel to the x and y axes. In other words, the product of the slopes of perpendicular lines is -1, and the only reason it doesn't hold for the x and y axes is because then you'd be dividing by 0 and slope is undefined. Okay, so let's prove this. So in the diagram, let the two lines with slopes m1 and m2 intersect at the origin. Okay? By the converse Pythagorean theorem, if the sum of the squares of the lengths of the blue and red lines equals the square of the length of the green line, then they must be perpendicular. Well, the square of the length of the blue line is 1 squared, which is 1, plus m1 squared, right? m1 squared. That's very simple. That's why we picked the origin as one of the points, because then the difference between this coordinate and the other point is just simply that coordinate itself. Similarly, the square of the length of the red line is 1 plus m2 squared. That's one of the beauties of the coordinates plane in calculating distances. The distance is basically always you can take the square of the difference in x and the difference in y, and that gives you the square of the straight line distance by the Pythagorean theorem. So it's important that you understand this theorem. If you understand how this derivation is working, you understand how to calculate distances in the coordinate plane. So what is this green distance between points m1 and m2? Well, the distance in x is 0, right? They're both at 1 and x. So the difference is the square of the distance between them is simply the square of m1 minus m2. Doesn't matter which order because we're squaring it, so it could have easily been m2 minus m1. So expanding this binomial, we get m1 squared plus m2 squared minus 2m1 m2. Okay, but now the blue length squared plus the red length squared, we calculated down here, we add these two together, we get 2 plus m1 squared plus m2 squared. So when the blue length squared plus the red length squared is equal to the green length squared, these lengths obey the Pythagorean relationship, and by the converse Pythagorean theorem, we must have a right angle. So this occurs when 2 plus m1 squared plus m2 squared minus m1 squared plus m2 squared minus 2m1 m2, which simplifies to, so let me rephrase this. This occurs when 2 plus m1 squared plus m2 squared equals m1 squared plus m2 squared minus 2m1 m2. So canceling things on both sides, this simplifies to 2 is equal to negative 2m1 m2. Divide both sides. They're perpendicular if the product of their slopes, m1 and m2, is equal to -1. So let's look at an example that might show up on a contest. If line AO with slope -1/2 intersects at the origin, point O, with line OB perpendicular to line AO, what is the y coordinate of point B if its x coordinate is 5? Well, how do we calculate the answer? Well, if this line OB is orthogonal to line OA, and they told us that the slope of AO was -1/2, we know the product of the slopes of perpendicular lines is -1. The slope of line OB must be 2. Okay, but they've told us the y coordinate, they told us its x coordinate is 5. It passes through the origin. If the x coordinate is 5 and a line has a slope 2, the y coordinate must be 10. So it passes, so point B must be at 5, So if the word mean just shows up, it is assumed to be the arithmetic mean. That's the average you know how to calculate. But there are other types of mean. There are harmonic means. We learned about them earlier in the course. There's also something called the geometric mean. We're going to get to that, but first let's look at this theorem related to right triangles. In a triangle with a right angle at vertex A, so we show that here, the altitude drawn from A to the opposite side, so that means this line A goes to point D, and it's the altitude, so it's perpendicular to line BC. This altitude divides the hypotenuse into two segments such that the products of the lengths of those two segments is equal to the length of the altitude squared. So this distance, AD squared, is equal to CD times DB. Why is that true? Well, triangle CAB is similar to triangle CDA by angle. Triangle CAB is similar to triangle ADB, also by angle. And therefore, triangle CDA is similar to triangle ADB by the transitive property of similarity. From the proportionality of the lengths of sides in similar triangles, we have the relations that the ratio CD to AD has to equal the ratio of AD to DB. So cross multiplying, CD times DB is equal to AD squared. So we've just proven this theorem. We could also express this as AD is equal to the square root of CD times DB. The square root of the product of two numbers is known as the geometric mean. If there are more than two numbers, the geometric mean can be generalized to taking the nth root of the product of n terms. So if you had 3 terms, you would multiply those 3 terms together, and their geometric mean would be the cube root of that product. If you had 5 terms, the geometric mean is the 5th root of the product of those 5 numbers. So a geometric mean is a different way of averaging terms than the arithmetic mean. And the reason it's called the geometric mean is due to its frequent appearance in geometric relationships like this problem. Let's move on to the exercises for this week. The first 4 exercises all relate to this figure. A regular hexagon centered at point O. We draw a rectangle around the hexagon by extending the top parallel edges such that the other sides of the rectangle pass through opposite vertices of the hexagon. Each side of the hexagon has length 12. What is the measure of any interior angle in the hexagon, such as angle ABC? Okay. 2. What are the measures of angle DBC and DCB? They're different. We want to know what each one of those measures is. What are the lengths of BD and DC? And finally, what are the areas of the rectangle and the hexagon? Let's move on to exercise 5. Line segment AB intersects the coordinate axes at 0, 8, and 4, 0. Okay, so at what point C, so this doesn't represent this diagram. So this problem 5, there's a line segment AB intersecting the coordinate axes at 2 points. It intersects the y-axis at 0, 8, and it intersects the x-axis at 4, 0. At what point C does a line segment passing through the origin intersect AB if that segment is perpendicular to AB? 6. Triangle PYT is a right triangle in which PY equals 66 and YT equals 77. If PT is greater than 50, what is its value expressed in the simplest form as some number x times the square root of y? So basically express your answer as an integer times the square root of another integer in simplest form. Exercise 7. The 2 centimeter long hypotenuse of an isosceles right triangle is also the base of an equilateral triangle. What is the sum of the areas of both triangles? 8. In the non-convex quadrilateral ABCD shown to the left, angle BCD is a right angle. AB is equal to 12, BC is equal to 4, CD is equal to 3, and AD is equal to 13. What is the area of quadrilateral ABCD? And finally, on to the challenge problems. In the figure below, we have a regular 12-sided polygon, known as a dodecagon, centered at point O. We form a triangle by connecting O to vertices A and C. If the distance AC is 4 centimeters, what is the area of triangle AOC? Okay, again, should check the numbering. This is problem 2. Angle C is a right angle. Point B is placed on side AC such that angle CDB is 45 degrees. If angle A is 30 degrees, what is the ratio of length BC to length BA? 3. In a rectangular prism with side lengths 3, 4, and 12, what are the lengths of all diagonals with integer lengths that can be found in the prism? And finally, question 4. Recall that the geometric mean of 2 numbers is equal to the square root of the product of those numbers. Prove that the arithmetic mean of 2 numbers is always greater than or equal to the geometric mean of 2 numbers. And then, what is the only case in which the arithmetic and geometric means are equal to one another? So that's it for this week. See you all next week.